Let's solve this exercise. Let's read. Suppose we have an electron, and this electron is accelerated from rest through a potential difference. So what we are imagining here is that we have two plates. Let me follow the same way that it's drawn in this problem. No? So now the negative plate is on the left, positive plate on the right. We have here our negative particle. We are holding it there. So initially at rest, and then we let it go and let it move by itself along its natural motion, which is to go to the positive plate, which is to lose potential energy, electric potential energy. Very well. They say that the potential difference between these two plates is 5,000 volts. Okay, so the potential difference, the high potential minus the initial potential, so the potential difference is 5,000 volts. And this is usually how they give us in the problems. They just give us the positive value of this potential difference because they give us in terms of the high minus the low potential. Okay, so 5,000 volts. And then comes the question, what is the change in electric potential energy of the electron? Okay, so we want to know what is the final potential energy minus the initial potential energy for this electron. We know that the potential energy, the change in potential energy is going to be negative because the electron will be losing potential energy. So I know that this result has to be negative. What we saw in previous lectures, in the previous slide, is that this change in potential energy is given by Q and final potential minus initial potential, right? That's what we saw. Let's go back to this slide. So the change, final potential energy minus initial potential energy is Q, Q multiplied by final potential minus initial potential. Okay, so that's what we are using to solve this problem. In this equation, this Q here, the sign of this Q matters. So, and this Q in our case is negative. Okay, now negative particle moves from moves from negative particle moves from low potential to high potential. So a negative charge moves from low potential to high potential. Remember, the convention is the plate that is more positively charged has high potential, the one that is less charged, more negatively charged, has low potential. Okay, so the negative charge will move from low V to high V. So the final potential is high and the initial is low. So this is really positive, right? Okay, so that's all we need to know. Now we just need to put the numbers there. The change in potential energy for this negative particle is going to be the Q. The Q is the Q for the electron. It's not written on this slide, but we know what it is, right? It's minus 1.6 10 to minus 19 coulomb, and the change in potential is the potential difference is 5,000. Well, we don't need to write there volts, but 5,000 volts. Okay, this will give us the change in potential, what the question asks, not the change in electric potential energy, which is going to be a negative value, and here it is, minus 8 10 to minus 16 joule. Okay, where did this energy go to? We lost potential energy. Where did it go to? It went to kinetic energy. No? So this change in potential energy went into this loss of potential energy went into kinetic energy. So the kinetic energy increased. It started from 0 because we had the particles at rest to a larger value, and so it became plus 8 10 to minus 16 joules. Okay, so this is the kinetic energy. The problem didn't ask the kinetic energy, but getting this value is useful for the question that is coming next. The question is, what is the speed of the electron as a result of this acceleration? Well, what is change in kinetic energy? Is the final kinetic energy minus the initial kinetic energy. Since the particle was initially at rest, this is 0. And this is 8 10 to minus 16 joule. Okay, what they want to know, what is the speed of the electron at the end after this acceleration? Well, here it is. This is what we want to get. And the mass of the electron, this one is given in this slide. Here it is. So if you put the mass of the electron here, you're going to get this final velocity, which is written here. Okay, so then we can solve the same problem for a proton. In the way they write the problem, they say here, if you read the book, now they say the proton would be accelerated from rest, same story again, but by a potential difference of minus 5,000 volts. That's not how it's usually written in a problem, okay? What they are telling us is already that the proton is going to go from high potential to low potential, but that's not how the problem usually gives us the potential difference. What the problems give us is a positive value. The potential difference between these two plates, the potential difference between these two plates is 5,000 volts. That's it. But in the case of the proton, we know that this proton is initially here in the region of high V, and it's going to move naturally to the region of low V. So if I write for the proton final potential minus initial potential, since the final is the region of low V, this will be a minus value. And what is the minus value? Minus 5,000 volts. Okay? Anyway, the rest of the problem is pretty much the same, because we know that this change in potential, and this potential difference is the change in potential energy divided by Q. So if we want to find what is this change in potential energy, which we can also write as delta potential energy, this is going to be Q, Q multiplied by the change in potential. Q in this case is positive, and this potential difference for the proton, the final minus the initial, is a minus value, minus 5,000 volts. This will give us again the same value that we had before for the potential energy. The change in potential energy will be a negative value because we are losing potential energy. 8 10 to minus 16 joules, because the charge of the proton is the same as the charge of the electron. Where is this energy going to? The kinetic energy. So the kinetic energy will be positive. And then, so this was question A. This is kinetic energy, is what we need to get the velocity of the proton at the end. How do we get that? The same equation again. Half of m v squared final minus initial. The proton was initially at rest, so if we put now the mass of the proton, now careful, the mass of the proton is different from the mass of the electron, is larger, and it's given in this slide, we are going to finally get the speed, the final speed for the proton. Okay, so this is the end of this problem.